So we are now talking about the batching and other data loader settings. So optimizing PyTorch data loader performance to reduce the cheap GPU idle time and make training faster is it's mainly focused on the batch size, the pinned memory, and the prefetch factor. So here's the core idea. A fast GPU is useless if it keeps waiting for the data from the CPU, and the data loader's job is to feed the GPU efficiently. So why data loader optimization matters? In deep learning, the CPU prepares for the data, the GPU trains the model. If the CPU cannot provide data fast enough, the GPU becomes idle. Training slows down, expensive hardware is wasted. So even after optimizing the number of workers, GPU idle time can still remain significant. So the goal becomes to reduce the GPU waiting time. This is done by tuning additional data loader settings. Next is batching. What is batch? A batch is a group training samples processed together. Instead of processing one image at a time, you process 32, 64, or 128, or even 256 images, like for example, at once. This is called mini batch training. So why batching helps? GPUs are designed for parallel processing. So like for example, in the transportations analogy, sending one passenger per car is inefficient, but sending many passengers in a bus is efficient because it reduces the congestion in the road. So that's the same idea in the deep learning. More samples processed simultaneously, better GPU utilization, and faster training. So batch size in PyTorch. So it says we have the data loader inside of the parameter is the dataset in batch size is 64. This means 64 samples are loaded together and the GPU processes all 64 simultaneously. And what happened when batch size increases? So we observed that small batches is slow training, but the larger batches is faster training. Eventually, performance stops improving because it exceeds its limits. Maybe it's a memory. So while larger batch sizes speeds up training, larger batches reduce the number of iterations per epoch, reduce forward, backward, and passes, improve GPU parallelism. Like for example, if we have the dataset of 60,000 samples, if batch size is 10, then there is 6,000 iterations per epoch. If batch size is 100, then there is 600 iterations per epoch. Fewer iterations means less overhead. So, but batch size cannot increase forever. The GPU has limited memory or virtual RAM or RAM. If batch size becomes too large, then GPU memory fills up, training crashes, or speed gains stop improving. So it calls as diminishing returns, meaning increasing batch size further no longer gives meaningful speeds improvement. Next is GPU saturation. So it says that once the GPU is saturated or memory bound, no further acceleration occurs, meaning GPU is already fully busy. Adding more data cannot make it faster. At that point, bottleneck shifts elsewhere. Maybe memory bandwidth, maybe CPU per processing, maybe storage speed. So key idea about batch size is the optimal batch size is the largest size that fits in GPU memory, improves throughput, and does not crash. Next is warm-up epochs. The lessons or in the previous lessons we have is repeated dimensions. First two epochs are warming up and the last three epochs are average. Why warm-up epochs exist? Early epochs are slower because the caches are empty, workers are starting, memory allocations happen, queue initializes, data pipeline stabilize. So measuring them would give misleading results. Next is memory cleanup. So memory is cleared after each experiment. Why? to prevent memory leaks. A memory leak means unused memory remains allocated. This means, or this can, slow later experiments, consume VRAM, cause crashes. Next is pinned memory or pin memory. This is one of the most important concepts. What is pinned memory? Normally, CPU RAM is pageable memory, meaning operating system can move it around, not fixed in physical memory. GPU transfer becomes slower because extra copying steps are needed. So pin memory is a locked RAM. When pin memory initialized to true, then PyTorch allocates special RAM. Data stays fixed in memory. Therefore, GPU can access it more directly. So the CPU and the GPU transfer is so fast now. There is no extra steps needed. So let's say we have the data loader. Inside of the parameter is a dataset, batch size, and the pin memory. Let's say batch size is 256 and pin memory initialized to true. So why pin memory can help? It speeds up the CPU to GPU transfer. This is especially useful when dataset is large, GPU is fast, many workers are used, training pipeline is complex. So the surprising result is experiment showed pin memory true was slightly slower. This confused many people, but explains something extremely important. So optimization context dependent, and optimization does not always help. Why pin memory true was lower? So the possible reasons is the dataset was small, the ciphertext is lightweight, transfer cost was already tiny, and the hardware was limited. Pin memory introduces its own overhead. On weaker systems, the overhead may exceed the benefit. Data pipeline was already efficient, so the GPU was already being fed fast enough, so pin memory gave little improvement. So here's the important principle. So optimizations are not universal. This is a major real-world engineering lessons. So the question is, should we still use the pin memory equivalent to true? The answer is yes, especially for larger workloads. Because in bigger systems, transfer latency matters more. GPUs are faster, parallel loading matters more. So here's the best practice. Usually, pin memory is equivalent to true is recommended when training on GPU, especially with number of workers that is greater than the 0 or its default values. So next is prefetch factor. So how many future batches workers prepare ahead of time? That's a parameter it controls. So in the data loader, we included the prefetch factor. Let's say it's equivalent to 2. So each worker prepares 2 batches ahead. So total preloaded batches is 2 times 6 is equivalent to 12 batches. That is number of workers in prefetch factor. It's equivalent to 12 batches. So why prefetching helps? While GPU trains on current batch, CPU prepares future batches simultaneously. This reduces GPU idle time, but there's a trade-off. The trade-off is larger prefetch factor means advantages, smoother GPU feeding, less waiting, and its disadvantages, it's higher RAM usage. So experiment results is increasing prefetch factor gave almost no improvement. Why? Because the data pipeline was already efficient. Extra buffering did not help anymore. So, and another important engineering principle is the lesson or the previous lessons know when to stop optimizing. This is extremely important in any real systems. Sometimes additional tuning, more complexity, and more memory usage gives almost zero benefit. So the recommended prefetch factor is prefetch equal to 2. It's usually a good balance. So overall, optimization is experimental. There is no universal perfect configuration. The best setting depends on hardware, GPU speed, CPU speed, dataset sizes, storage speed, augmentations, RAM, and operating systems. So Summarize number workers, its purpose is parallel CPU loading, batch size is GPU parallel processing, pin memory is faster to GPU transfer, prefetch factor future batch buffering. So a well-optimized data loader can cut seconds of an epoch. So examples in the real training, if you have 5 seconds per epoch and the training uses 10,000 epoch, you save 50,000 seconds. That is approximately 13.9 hours. So batch size control samples processed together. Larger batches improve GPU parallelism. Too large causes memory issues. The pin memory speeds up CPU to GPU transfer, useful for GPU training, may not help on smaller systems. And prefetch factor, workers prepare future batches early, reduces GPU idle time, but it's too high wasted RAM. So measure performance, experiment carefully, stop optimizing when gains become negligible.